Welcome to The Deep Dive. Today, we're looking at one of humanity's biggest scientific leaps, the James Webb Space Telescope, JWST.
An incredible machine.
Absolutely. And our guide is Richard Panek's book, Pillars of Creation. He uses that famous Eagle Nebula image, the pillars.
Right, as a sort of doorway.
Exactly. A doorway into how JWST hasn't just changed what we see out there, but fundamentally how we see it. And that changes what we can know.
It really does. It's physics, engineering, amazing discoveries, and a very human story behind it all.
So our mission today is to unpack all of that, how this telescope shifted our whole cosmic perspective.
Yeah, it's been transformative, even in just a few years. New eyes on the universe, basically.
Okay, let's dig into it. We've all seen those JWST images, right? They're stunning. But how is it actually different from Hubble? Why infrared? Why does that matter so much?
That's the crucial question, and Panek explains it really well. Infrared is key for, well, a few big reasons.
Okay.
First, seeing through dust. Space isn't empty. It's got these clouds of tiny dust grains.
Right, the stuff that blocks starlight.
Exactly. Visible light gets scattered or absorbed. But infrared light, it goes right through. It's like having X-ray vision for dusty regions.
Ah, okay.
Yeah.
So you can see inside places like star nurseries, like the pillars themselves.
Precisely. Places that are just dark silhouettes to Hubble suddenly reveal the baby stars forming inside when you look in infrared. You see into the clouds.
That makes sense. What else?
The second reason is maybe even bigger. It's about seeing the very early universe.
Cosmic dawn.
Yeah. The universe is expanding, constantly stretching. So light from the most distant, earliest galaxies, we're talking light that left maybe 13 billion years ago.
Wow.
That light started out as visible or even ultraviolet, but it's been stretched so much on its journey to us that it arrives as infrared light.
So it's redshifted.
Highly redshifted, like galaxies are redshift 10, 11, 13. That's the universe when it was just a few hundred billion years old. To see that cosmic dawn, you need infrared. There's no other way.
So it's a time machine, basically, looking back almost to the beginning.
In a very real sense, yes. And the third reason, it's technical but vital, heat.
Heat.
Infrared light is heat radiation. So the telescope's own instruments, if they were warm, would just glow brighter than the faint objects they're trying to see. They'd blind themselves.
Ah, I see. So it has to be incredibly cold.
Extremely cold. That's why it has that enormous sun shield, the size of a tennis court, 5 layers thick, to block heat from the sun, earth, moon.
And why it's way out at L2, right? Far from Earth's heat.
Exactly. 1.5 million kilometers away. And some instruments, like MIRI, have to be even colder, using a special cryocooler to get down to just 7 Kelvin.
7 Kelvin. That's unbelievably cold. Colder than Pluto.
Pretty much. Just a few degrees above absolute zero. A huge engineering challenge.
And these instruments, they're specialized, right? Panek highlights them. NIRCam, NR spec.
Yes, each does something different. NIRCam is the main camera for near-infrared. It takes those amazing deep-field images and pictures of star-forming regions, the eyes. Then NR spec is the spectrograph. It splits light into its component colors, like a prism. That tells you what things are made of, how fast they're moving, their redshift.
And we can look at hundreds of objects at once.
Yeah, using this amazing microshutter array. Tiny little windows it can open or close to target specific galaxies, a real game changer for efficiency.
And MIRI, the super cold one.
MIRI sees mid-infrared light. That's even longer wavelengths. It's great for seeing warmer dust, complex molecules, and jets shooting out from baby stars, things an NIRCam might miss.
And there's a Canadian instrument, too.
Right, NIRI-SFGS. It does fine guidance, keeps the telescope pointed perfectly steady, but also has modes for studying exoplanets and other bright things. It's a whole suite working together.
So the science is incredible, but Panek really emphasizes the journey to get it working. He calls the deployment a 29-day space thriller.
Oh, it absolutely was. I mean, think about it. Launched on Christmas Day 2021.
I remember that.
On an Ariane 5 rocket, headed way out to L2. And the key thing, no second chances. No astronaut repair missions like Hubble had.
Right, it's too far away. Everything had to work perfectly the first time.
Everything. Hundreds of potential single-point failures, hinges, latches, motors, antennas. If any one critical step failed, the whole $10 billion mission could be lost.
That's terrifying. What were the scariest parts? The sun shield.
Definitely the sun shield deployment. Those 5 enormous, fragile Kapton membranes, each thinner than a human hair. They had to unfold perfectly, separate, and then be tensioned precisely using dozens of motors and cables.
Like the most complex, high-stakes origami ever.
Pretty much. For days, everyone was just holding their breath. Any snag, any tear, disaster. Panek captures that tension really well.
And then the mirror unfolding, that giant golden honeycomb.
Yeah, the A2 beryllium segments, they launched folded up. They had to swing into place, lock, and then be aligned with microscopic precision.
Using wavefront sensing.
Right, basically measuring how light reflects off each segment and sending commands to tiny motors on the back of each one to adjust its position and tilt. Nanometer precision.
To make 18 small mirrors act like one giant, perfect 6.5-meter mirror.
Exactly. And don't forget, the cryocooler for MARI had to start up and work flawlessly, too. It was just step after step of critical moments, and unbelievably, it all went perfectly.
A triumph of engineering. And Panek points out it wasn't just NASA, right?
And now, a huge international effort. NASA, the European Space Agency, the Canadian Space Agency, years of collaboration, surviving budget cuts, political fights. It really is a testament to what international cooperation can achieve.
Okay, so this incredible machine gets deployed perfectly. What has it actually shown us? It feels like discoveries are pouring out constantly.
They really are. And what's fascinating, as Panek shows, is how it's giving us new insights across all scales, from nearby star formation to the edge of the observable universe.
Let's start with the book's namesake, The Pillars of Creation. Hubble's image is iconic. What's new with JWST's view? Is it just sharper?
Oh, it's so much more than sharper. Hubble saw these majestic, dusty silhouettes. JWST, especially with an IR cam, pierces through the dust.
And sees what's inside.
Exactly. You see newly formed stars inside the pillars, those telltale diffraction spikes pinpointing them. You see these little knots called AGs, evaporating gaseous globules, which are like cocoons where stars are incubating.
Wow.
And you see the process happening. The intense radiation from massive young stars nearby is literally boiling away the gas at the tips of the pillars. It's called photoevaporation. You can see it sculpting them in real time almost.
So it's not static, it's a dynamic environment.
Highly dynamic. Star birth and destruction happening side by side. And MRI, in the mid-infrared, even reveals jets shooting out from some of the newborn stars' Herbig-Haro objects. We're seeing the anatomy of star birth, not just the silhouette.
That's incredible. Moving from our galaxy's backyard way, way out, cosmic dawn, the first galaxies. What's the big surprise there?
The surprise was finding so many galaxies and finding them looking surprisingly, well, developed, I guess, at incredibly early times.
Earlier than expected.
Yes. Deep field images found candidates at redshifts higher than 10, even up to 13 or more. That means light from less than 500 million years after the Big Bang.
Okay.
And NR spec confirmed these redshifts. The shock was that some of these galaxies seemed quite bright, maybe even with hints of structure, like disks, forming much faster than most models predicted.
So star formation got going really early and really efficiently.
It seems that way. The number of bright, star-forming galaxies back then, what astronomers call the UV luminosity function, appears higher and extends to brighter galaxies than we thought.
What does that mean for our models of the universe? Does it break cosmology?
Panek is careful here.
Yeah.
It doesn't really break the standard lambda CDM model of cosmology, but it does challenge our understanding of galaxy formation within that model. Our recipes for how quickly gas turns into stars, how galaxies assemble, they might need significant tweaking.
So the basic physics holds, but the details of how structure formed were perhaps faster, more efficient.
Something like that. It also means these early galaxies might have played a bigger role in cosmic reionization, burning off the primordial hydrogen fog than we assumed. JWST is forcing a rewrite of those early chapters of cosmic history.
Okay, from the biggest scales to, well, other solar systems, exoplanets. How is JWST changing that field?
It's completely revolutionizing it. We've gone from just detecting exoplanets, knowing they're there, to actually studying their atmospheres in detail.
How does it do that?
Primarily through transmission spectroscopy. When a planet passes in front of its star, some starlight filters through the planet's atmosphere on its way to us.
Ah, and the atmosphere leaves its fingerprints on the light.
Exactly. Molecules in the atmosphere absorb specific wavelengths, specific colors of infrared light. JWST is incredibly sensitive at picking out these absorption features.
So we can tell what gases are there, like water, carbon dioxide.
Precisely. We've had spectacular successes already. WSB-39b showed the first clear detection of carbon dioxide on an exoplanet, plus water, sulfur dioxide, a really rich atmosphere. LOFS 96b gave this beautiful, clear signal of water vapor, almost textbook perfect. And for systems like TRAPPIST-1, with its Earth-sized rocky planets.
Yes. What about those?
It's harder there, the stars are more active, the signals are tiny, but JWST is starting to put real constraints on whether those planets have atmospheres, and if so, what they might be like. It's a huge leap towards assessing habitability.
Towards maybe finding biosignatures one day.
That's the long-term dream, yes.
Yeah.
JWST is giving us the tools to start that search seriously.
Amazing. But it's not just looking light years away, is it? Panek mentions it studies our own solar system, too.
Absolutely. And it's produced some stunning results close to home. Incredible views of Jupiter, its auroras, its faint rings, the details in its storms.
I've seen those. Amazing detail.
And Neptune and Uranus. We're seeing their rings and atmospheres with clarity we've never had from Earth, tracking clouds, seeing seasonal changes.
Even things like asteroids and comets.
Yes. Measuring the composition of ices and organic molecules on these small bodies. That tells us about the building blocks of our solar system. It's even observed Saturn's moon Titan, tracking methane clouds. It really is an all-purpose observatory.
Which brings us back to the images. They are just so beautiful. But how are they made? Is it false color? Is it just artists making things up?
Panek tackles this really well. It's definitely not arbitrary. It's a process, he says, from data to science to art.
Okay.
The raw data from each infrared filter is monochrome, basically black and white. The teams then assign visible colors, usually blue to shorter infrared wavelengths, green to medium, and red to longer ones.
Ah, so the colors represent different types of infrared light.
Exactly. They represent real physical information. Red might show cooler dust or molecular hydrogen. Blue might show hotter stars or ionized gas. Panek prefers calling it representative color because it encodes physics.
That makes sense. It's translating invisible light into a visible language we can understand.
Precisely. And the data processing pipelines are public now. Anyone, scientists or citizen scientists, can download the raw data and try processing it themselves. It's transparent. These images are, as Panek puts it, like compressed knowledge, visual summaries of complex reality.
Okay, so pulling this all together, beyond the specific discoveries, what's the deeper takeaway here? What's the philosophy Panek finds in the JWST story?
I think a key point is how each new observational tool, Galileo's telescope, Hubble, now Webb doesn't just answer old questions, it forces us to ask entirely new ones we hadn't even conceived of before.
It expands the horizon of our curiosity.
Totally. And also that the process of discovery is deeply human. JWST wasn't just built by equations and circuits. It was built through decades of struggle, budget fights, political maneuvering, brilliant problem solving, and sheer human persistence and collaboration.
That human element is crucial.
Panek argues that how we know is inseparable from the instrument and the people behind it. The failures, the risks, the teamwork. They are part of the knowledge gained.
Which connects back to the pillars of creation, the metaphor.
Exactly. He suggests knowledge itself condenses, like stars in a nebula, out of the friction and turbulence of human effort and collaboration. JWST itself is like a pillar of knowledge created by humans.
That's a powerful idea. So this deep dive, guided by Panek's Pillars of Creation, really drives home how JWST has just fundamentally shifted our view, from star birth nearby to the first galaxies to alien atmospheres.
It's a testament to ingenuity, collaboration, and that relentless human drive to explore, to understand.
We've definitely moved from asking what if to actually observing what is in ways that were science fiction just a generation ago.
Pushing boundaries constantly. It's humbling, really, seeing the universe unfold like this.
So here's a thought to leave you with, sparked by Panek's metaphor. If knowledge, like stars, condenses from the friction and turbulence of human collaboration, and JWST is one such monumental condensation, what other pillars of knowledge do you think humanity is capable of building next? What new mysteries might our collective curiosity and determination sculpt from the cosmic dust, or perhaps from challenges right here on Earth? What does this incredible achievement tell us about our own potential? Thank you for joining us on this deep dive.